In this video, we're going to look at the definition of accumulation point for a set M, which is a subset of the real numbers. This is one of the most important definitions that we will have in the entire semester. So it's important that you really understand this definition because it is a subtle definition. The definition given in our textbook looks like this. You should stop the video, copy this definition carefully in your notes, and think about what it is saying as you're copying it. So hopefully you've done that. So let's start trying to pick this definition apart. The first thing that I want to realize is that we've got some quantifiers. P is an accumulation point for M if every, that's a quantifier, open interval containing P also contains, there's an implicit quantifier there. We have to contain a point of M that is different from P. Now, if I want to write this more symbolically, I have to actually start putting some certain things in. The if and only if is because this is a definition, and every open interval, we're going to give the open interval a name that contains P. That's what P is in O means. There is an X inside the open interval such that X is in M. Take away P, and this take away the set containing P is how we're saying symbolically that this point of M is different from P. So what I want to do is I want to actually try and draw some pictures that illustrate what this definition means. So let's draw a number line. So here's my number line. And I want to illustrate what we mean when we say let P be an accumulation point for the set M. Now, I'm actually not going to draw M in this picture because I don't know what the set M looks like. I'm going to focus, however, on P. Now, the first thing is that we have this quantifier for every. That is actually a for all quantifier. So for every open interval named O with P inside O. So I need to draw an open interval. Okay, here's an open interval. For every one of these guys, we can find means there exists somebody inside that open interval with that somebody being inside the set M and that somebody not being equal to P. In other words, coming back over here, inside this open interval and not equal to P, there's got to be an X inside of set M. And now I want to notice that I can stick another open interval. I can make a smaller open interval. Here's a smaller open interval. Let's call this one O prime. O prime is an open interval, and P is certainly in O prime, so there exists, I'm going to call it an X hat inside O prime, such that X hat belongs to M and X hat is different from P. So in other words, I can come in and I can put in there's X hat. And I can keep doing this with one interval after another interval after another interval after another interval. We'll look at that in a few minutes in a little bit more detail. But it's also important when we have a nasty definition like this that we understand what it means if something is not satisfying that definition. So what I want to do right now is I want to turn my attention to the flip side of this. What does it mean when we say that the point Y is not an accumulation point for m. Now, I can think in terms of purely dealing with the symbolics, but I'm actually going to try and get this through number lines. So over here, I'm going to be thinking in terms of what it means to be an accumulation point. And over here, I'm going to be thinking about what it means to be not an accumulation point. And we're going to start with number lines on both of these guys. So over on this number line, I've got a P, and P is an accumulation point for M. So for every open interval containing P, that's a new symbol. It's a backwards is an element of, and it simply means containing. So for every open interval containing P, there exists an X inside O intersect M. In other words, this puts X inside M and O, and X is not equal to P. So if I draw an open interval, there is somebody inside this interval that is in M, and that guy is not equal to P, so there's space there. Now, if I think about trying to figure out the negation of this, so I'm going to say Y is not an accumulation point for M. What does that mean? Well, it means that we have the negation of, for every open interval containing Y, there exists an X inside this intersection, and X is not equal to Y. Now, to negate that thing, we're going to negate it one step at a time, and then we're going to kind of figure out how to draw this. So the negation of a for all statement is a there exists. So we are looking for a specific open interval that contains Y. So here is Y, and here is my magic open interval. I'm going to denote this guy as O hat. So this picture is for any O, and this is for a specific O hat. And then the negation, the rest of this negation is going to be, so for this, we have to negate the statement, there exists an X inside our open interval intersected with the set M, and X is not equal to Y. Now, if I carefully look at how to negate this particular quantified statement, the next thing that we're going to get is there exists this O hat that contains Y, such that for every X inside this guy, we have to have X is equal to Y. Now, technically, this does not mean, so it's important to understand, this does not mean that Y has to be inside M. This statement says if X is inside O hat intersect M, then X is going to have to be equal to Y. In other words, coming back up to my number line, this is the only possible, let me put this in another color, Y is the only possible element of M in this entire whole interval. So Y is the only possible element of M inside the open interval O hat. So what this basically boils down to then is the following, and I want to kind of clean up the picture. Y is not an accumulation point for M means one of two things. We have this number line or we have this number line. On this first number line, here is y, and over here, here is y. We have some interval O hat, so there exists an O hat that is an open interval, and it contains 1. And that's going to be true in both of them. So over here is my O hat. And over here, we're going to say, and y is the only element of M that belongs to the open interval O. So in other words, this is the only guy inside M. So what does that mean? That means there are no elements of M in either of those two intervals. Our second case is y is not inside M. And what happens then is that when y is not an accumulation point, the intersection of this open interval and the set M must be empty. In other words, over here, there are no elements of M. Now, it turns out that we're going to have one more definition. This case over here, we call y an isolated point of M. So I want to finally clean this up with one definition of what an isolated point is, and then we will call it the end of the video. So y is an isolated point of M means y is in M and y is not an accumulation point. And the picture for an isolated point, and let me draw a proper number line. The picture for an isolated point is here is y and y is inside M. But if I look at an open interval, I can find an open interval that contains y such that M intersect that open interval is equal to the singleton set containing y. In other words, there's space between y and the next nearest element of M.